thank you very much, Paul, for this introduction. And typically, it's also customary as the last talk of a 2-day conference to say we've saved the best for last, and indeed we have saved the best for last. So for those of you who are familiar with the Excellence Cluster at the HGI, you would be very familiar with our CASA fund. And to keep the excitement and the motivation going for the next 45 minutes, we will be giving away this CASA fund to the first person who will have their first question in the Q&A session at the end of our 45-minute talk. So, on your mark, get set, go. All right, so in the next 45 minutes, we're going to present a collaboration that Rafa and I, together with his supervisor at the time, Claudia, and still postdoc supervisor, worked on. And we tried to understand whether we could actually put together an Android malware classifier that was privacy preserving and at the same time leveraging this concept known as federated learning. So we are aware that this is probably the only mobile security and privacy talk for the whole conference, and there's also quite a bit of sort of heavy machine learning techniques involved. So we would try to introduce the basics as we go and at the same time explain the contributions that we've made in this field. All right, so I will start with giving a little bit of background knowledge, the motivation behind this work, how we actually even ended up working on this problem, and then Rafa will take over and talk more about, how we actually leveraged federated learning to build this privacy-preserving malware classifier. All right. So I think with the audience that we have here, I do not need to explain to you why malware is bad, but the question is, why should we still care? So what you see here is sort of a collection of articles that we keep seeing in the media day in, day out. And the reason why we should still keep caring is as technology evolves over the years, so do the malware that we keep seeing in the wild. So this means the game is not over, the adversaries are still out there, and we need to still adapt our solutions for the new malware variants that we keep seeing, for the new technologies that are out there or that we expect to see coming in the future. So, and at the bottom you will see, we all know Windows malware, Linux malware, and now what we're seeing are variants of Android malware that we have been seeing in the past, but targeted to IoT devices or any smart devices that you would deploy in a smart environment. All right, so the issue is still there, so how do we move further with this problem now? We also expect things to not go away anytime soon, partially because Android remains the preferred mobile operating system globally. So what you see here is sort of a comparison between the Android versus iOS global market share. And although iOS is very far below, I should also mention that in countries such as the US and the UK, iOS is the preferred operating system, but for the rest of the world, Android remains the clear winner. So we all associate malware with security problems. However, what we're also noticing is those malware are turning our security problems more towards privacy issues. So in the past year, a lot of the malware variants that were detected by antivirus companies were actually exploiting what are called PII, so personally identifiable information. So at the top here, the first 100% says Android malware families show PII selling capabilities, including or leading to app fraud. So the APP fraud here stands for authorized push payments. So think of these cards that you store on your phones, any payment forms that you store on your phone. These are actually being exploited by malware as well to sort of trigger payments in the background that will lead to the benefits of the adversary, so in terms of monetary benefits. So it's a combination of exploiting security vulnerabilities, but also leveraging user data to do the exploit in the wild. So before we start bashing Google and Android, it is also fair to maybe highlight what they have done or tried to do in the early days to try to address these security problems. So in the early days of Android, Google said, okay, we know we have this new operating system and we will also have security measures to prevent any attacks. So they tried to apply this, what I call three-pronged approach. So that's usually the vetting process, something called a permission system, and then leveraging the sandboxing technique. So for those of you who are not familiar with these approaches, so the vetting process is essentially a way of verifying, so procedure to verify apps that are uploaded by developers, and they request for these to appear or be uploaded on the official Google Play Store. These apps first get vetted, so analyzed by Google engineers to see if these are potentially malicious apps. What are the finer details of this vetting process? That's still a mystery. What do they actually check for is still a mystery. To what extent is this analysis is also still a mystery. So there are, let's say, some chatter on the web that says maybe they use a hybrid approach that is sort of static and dynamic analysis combined, execute this in a sandbox, and then if there is no malware that gets triggered, then they will classify this as okay to be uploaded on the Play Store. Having said this, there has been research already done that showed malicious apps can get on the Play Store. Doesn't matter whether it's free or paid. They have used techniques to show, okay, what actually triggers flags during this vetting process and what doesn't. So this can be circumvented as a form of security measure. The next one is the permission system. So if you are an Android user, perhaps permissions ring a bell to you. So in the early days, when a developer would write an app and they would need access to certain, let's say, what is referred to as restricted resources, so logs, address book of the user, location information of the user, they will need, or they were required to also request for the equivalent permissions in the manifest file and declare this here. So in this example that you see, so there are phone calls, and for accessing or allowing phone calls to take place, this means you need, as your app needs to read the phone, state, and identity of the phone. So the equivalent permission of this is called android.permission.read_phone_state. So each of these, let's say, protected resources had an associated permission with it, and all of these are actually part of the Android developer documentation, and they know when, for which permission they need to request certain permissions. Again, the bad side of this, so there has already research shown that developers tend to request more permissions than necessary. So there was no mechanisms to prevent developers from requesting 100 permissions without actually needing these 100 permissions. And what this led to was essentially allowing attackers to do what is called privilege escalation attacks, because these permissions, remember, give you access to restricted resources. So therefore, they would exploit the overuse of these permissions to carry out their attacks. And thirdly, sandboxing. So this is sort of the literal meaning of what we know a sandbox does. So the idea is to provide security by isolating the app processes. So apps are usually referred to with an ID when they're running on the phone, and the security mechanism here is as long as each app is running within their own sandbox, therefore it would be difficult to exploit information or any sensitive data that's being executed within certain sandbox to be leveraged by other apps in a different sandbox. However, here Google also understood that there needs to be interoperability, which was the sort of the key word of this year's conference. So here, to allow this to happen, there was what is known as the inter-process communication, and it can be done through a mechanism called intents. And again, we go back to privilege escalation attacks. There has been work already shown that you can actually leverage this intent mechanism to talk between different sandboxes to carry out attacks. All right. So this is what was done in the early days, what has already shown to be broken. But Google still kept up with everything that was being published, every security vulnerabilities, misuse of their mechanisms that they came up with in the early days, and kept improving things. And more recently, they announced this functionality called Google Play Protect. They said, okay, we know things have not been done properly in the past, and we acknowledge this. However, we now have the golden solution for you all. So with Google Play Protect, we're going to actually push this to all Android devices as a functionality. And what it will allow you to do is essentially allow us to scan your apps remotely and be able to remotely detect the presence of malware on your devices. Fair enough, when you hear this, you're like, okay, they of course don't want to give more business to antivirus apps, so they are going to do this themselves. And they anyway have access to the corpus or the large data set of apps, so why not do this themselves? So this is essentially some kind of antivirus functionality. And then as you read further, you then notice that they not only scan apps that you installed from the official Google Play Store, but they also are scanning apps, or claim to be able to scan apps that you installed from what they call unknown sources. So as an Android user, you would also know that you can install apps from the official Play Store, and that's actually the recommended way of installing apps, but you can also install apps from third-party app stores. And Google claimed that they can even scan these apps. So from here, it sounds too good to be true, right? So you not only can access things that I download from your host Google Play Store, but you can also, know which apps I'm installing from third-party app store. So then that sort of raised an alarm, and you're like, okay, how would Google actually implement this? So things start to slowly get more and more interesting. So as you read through the documentation, the magic M words appear. So they are using machine learning to do this. So you dig through the documentation. So there is a blog post where they say we're going to keep 2 billion Android devices safe with machine learning. And then you start reading the details of this machine learning. It says machine learning means training a computer algorithm to recognize a behavior. To train the algorithm, we give it hundreds of thousands of examples of that behavior. Okay, you have these examples because you're also hosting the Google Play Store. In case of Google Play Protect, we're developing algorithms to learn which apps are potentially harmful and which are safe. So they are using machine learning to develop algorithms. So again, once you start to dig deeper, you're like, okay, you are scanning 2 billion devices on a daily basis to learn particular behavior and also remotely be able to identify malware. So which means you are learning more that you need to be able to do this kind of service to the users. So we started asking this question, okay, could we do the same thing without using these harmful techniques that Google is using? So essentially, can we take the monopoly away from Google? Could we do the same thing by just not be able to scan billions of devices on a daily basis? And that also led to the question, what kind of information would you need access to be able to do this in a privacy-preserving manner? So we all know we want users to be secure, but also what data do we exactly need to do this to provide privacy guarantees? So here, there is a technique which is called Federated Learning. So for those of you who have never heard of this term before, I would like to introduce it using an example. So if you have typed on a phone and a tablet before, you would notice that there is this functionality of predictive typing. So whenever you type one word, immediately you get suggestions for what your follow-up words would be. So the question here is, what is the mechanism behind this for predicting these words? And the way that Google does this is essentially learning typing behaviors over all the users across the devices and then pushing these to do these word predictions on users' phone. So this is essentially what federated learning means. So you are doing, it's also referred to as collaborative learning, and essentially what it means, you are learning in a distributed manner. So this term was introduced and coined by Google in 2017, and they also had a publication that you see on the top right there. And before Rafa takes over and explains to you the mechanics, so some more technical details about this, I would like to give you an overview of what the framework of this federated learning approach looks like. So for now, you can ignore all the mathematical notations, so we won't dig deep into this. All I want you to focus on is the actual let's say, flow of information. So if you follow the numbers, so like I said, the goal here is to learn in a distributed manner, so which means you will be leveraging the knowledge from various, what we call local clients in our work. So these local clients, in our case, are here. So in the case of the predictive typing, you can think of all these local clients being in the form of phones or tablets. And then to allow federated learning to take place, as a first step, you will need to load a model on each of these devices so that they will then get trained on the user data. So keep in mind here that whoever is in control of the global server here has no direct access to the data of the user. So we push the machine learning model to the local devices. They train using local data, and then after a certain amount of time, they will then send the updated model in aggregated form. So again, we cannot infer any data at this point about users' particular device back to the global model, and this gets aggregated, the update gets pushed into the model, and then you do several rounds of what is called federation. So you learn iteratively over time by leveraging the data from the local clients. So Rafa will tell you a little bit more about how we then exploit this mechanism to do malware detection. So this is mostly related to, okay, how would that work in sort of predictive typing setup? But how would you do this in malware, in a malware detection context? So for those of you who are familiar with sort of the traditional classical malware detection pipeline, this can be classified into 3 phases. You have usually the feature extraction phase, the feature representation phase, and then you have prediction inference. So this is sort of the classical way of doing malware detection. You collect your samples, you extract features. There are different ways of representing these features. So we treat those as a black box for now, and then you can apply either clustering algorithm or other form of classification algorithm to identify and detect malware. So the question is then, how do we move from this classical approach to this setup, so the federated learning setup? And now I'm going to give over to Rafa.
Thank you.
I think you did not want this, right?
Can I? No, that's okay. The clicker. Yes. Hello. So, okay, Veelasha introduced why do we care about malware? Why do we use machine learning? And the problems. The problem is that now Google is collecting a lot of data from us that they don't need. How do we solve this? We use federated learning to basically create a self-evolving, privacy-preserving malware classifier. Self-evolving because what Veelasha explained about the rounds, new users install new applications, and you keep training the model. every round, and then you get a better model every day that you train the model. The challenge that we solve is data minimization. Now we don't share data, we share only parameters. So for us in this talk, a model is a set of parameters that you can use to apply a function and predict something. In our case, if an app is malicious or clean. So of course, as a solution, it's very nice. You solve the data minimization problem, you only share parameters. But of course, there are assumptions and risks. The main assumption for us that is very important is that you assume the users have labels. That means the users know what the machine should predict correctly. In the case of typing, it's obvious. So you know what you are typing. The machine will make a prediction. You will say, this is correct. And the machine will say, OK, my prediction was good. Keep learning like this. If the prediction is wrong, you will not choose the prediction that the machine gives you. You will choose something else. And the machine will learn that it made a mistake and change its parameters to next time predict better. But of course, in malware, we don't know that. We don't know if an app is malicious or not. So we cannot assume we have labels. We cannot assume we are in one of these cases where we have labels here. We don't have that. And there are also additional risks. The main two for us as security, and privacy engineers is inference attacks and poisoning attacks. So with federated learning, we can solve the privacy problem by sharing parameters. But what if in these parameters we can identify the data that we are trying to protect? Those are called inference attacks. On the other hand, now you don't have a central service that you can collect data, sanitize it, and produce a nicely fit model. You have a bunch of users sharing parameters with you. You don't know who, you don't know how. So this gives avenue to attackers who can compromise users and submit wrong parameters on purpose to make the model fail. For example, if I'm a malware vendor, I'm trying to make my malicious app become clean to the Google Play Protect engine, I can train my local model in a way that says my application, malicious application, is clean. Then I poison the model. With this, we break performance. How does this work? For inference attacks, it's actually pretty simple. So each user will send a bunch of parameters. So these local updates is a bunch of parameters. You can imagine a matrix with many numbers. And the adversary will be able to see them and say, OK, when this set of parameters are updated, that means that this user installed this app, or this user typed this word. Because there is such a number of parameters that there are unique combinations per possible candidate of examples. So if you can calculate this difference round per round, you can analyze what new data the user provided to the model in that specific round. So yeah, you are protecting data, but you are still vulnerable to this kind of attacks. For poisoning attacks, this is actually a security attack. So you can break performance. You can do it in two ways. Normally, in a centralized model, we care about data poisoning. So somebody breaks into my database and poisons my database. And so now it says, all my data is clean data, clean apps. In federated learning, you don't have such a problem because you don't have data yourself. It's the users who have the data. But you can poison very easily the model, the parameters themselves. In a centralized model, these parameters are trained by the service provider and nobody has access to them. In the case of federated learning, they do have access because it's the users themselves who are submitting these parameters. So an adversary can compromise a set of users and submit wrong parameters. So this is what we will look into in this talk. Our solution to these two problems and the assumption is called less is more, or LIM for short. And we basically leverage a new kind of machine learning. It's not supervised, it's not unsupervised, it's a semi-supervised machine learning model where users can be trained without labels, without knowing if an app is malicious or clean. You can still train it, you can still get better performance. And most importantly for us, we address inference and poisoning attacks. we basically do this with two mechanisms. First, we make this huge set of parameters that enables unique fingerprints of examples to be much smaller. So now we have a very small set of parameters, and it's difficult to pinpoint specific examples in those parameters. And for the poisoning, we have a method to offset the outliers. So if I'm an adversary poisoning the model, we in LIM have a way to get rid of those influences and still get a functional model. Let me first introduce a little bit what is semi-supervised learning. So normally we have labeled data. Everything is labeled, so you learn perfectly what is the optimal decision boundary. If you don't have all labeled data, you don't know the labels, then you will have some labeled data and some not labeled data. For us, the proposal is to use the unlabeled data given these two assumptions. So we can assume that examples that are close in feature space, that have similar numbers in their vectors, share the same label. And the different classes, in our case, malware and clean, they have very different patterns. So you can just draw a line between them very clearly. The way we use this, we achieve this, is using ensemble learning. So you may have heard about one classifier that you can use. In this case, we use multiple classifiers together, combined. How do we combine them? We basically assign weights to each of the classifiers and have a function to aggregate their predictions. In this way, we can try to improve performance using unlabeled data, because you may ask, how can you learn from data that you don't know if it's malware or clean? How can that improve? There is a branch of semi-supervised learning called SAFE, semi-supervised learning, that exactly tackles that problem and uses fancy math that I will not go into in here to assuming that the correct prediction is somewhere in this ensemble of classifiers, you can still get an improvement over a baseline classifier. So this is exactly what we use in LIM. So the semi-supervised model that we use was centralized. Again, you share all the data with the cloud. They have a fancy semi-supervised model, and they use it. We don't want that. We don't want to share the data. So we will put those models in each of your smartphones. Your smartphone will train a unique model with your own apps. But for us to learn together, we will share these parameters of this model with a cloud. And the cloud will only get this set of parameters. These parameters go back once they are aggregated, and we keep on going. So I will go slowly over these steps to understand how this works. So first of all, we train this ensemble of classifiers. We have multiple classifiers. We have to train them, and that we do on the cloud. There's no personal data there. It's OK. There are a bunch of questions that we need to ask, which basically give room for further work, to future work. But at the end, we use a small number of models, specifically because our number of parameters is exactly the same number as the number of classifiers. So we only have 5 parameters. Our model is 5 numbers. That's our model. This is what we call security and privacy by design. We started from the very beginning thinking about how can we address these privacy and security concerns. For performance-oriented people, you may ask, okay, how can we get the best performance? We didn't look into that question yet. We used only very standard models, vanilla models. But there is, of course, room for improvement for specific applications. After the cloud has trained a bunch of models, they share them with the clients, and now the clients will use their apps. Will use their apps to estimate the parameters of their model. So remember, we have a set of models. We have a model that was shared by the cloud. We install new apps, and these apps make the parameters of the model change, even without labels. To federate, we not only use our own weights, our own labels, but we also our own data, but we also use data from the cloud. So once the cloud can share data with us, we can average those parameters to get a federated model. Those parameters enable us to predict locally. So malware or clean is decided locally in your phone. And now we can share the new parameters with the cloud, with the service provider. It's important to take into account, to remember that these parameters are just 5 parameters. This is what we share. This is how we address the privacy and security concerns. Once we have that, the cloud can average all the client parameters into one set, and then also averages it with our own set of parameters. The cloud also trains its own semi-supervised model and averages these parameters. And then at the end, they share. The cloud shares the parameters back to the users. The users take them and restart the process. At any time, the cloud may retrain base learners. That means basically sharing a new set of models for the ensemble and share them. So, okay, we have this fancy system. How do we know it works? This is complicated, okay? This table, you should not read it. This is a table from the Wikipedia page, very complex. Everybody goes there to check. There are many metrics. It's difficult to use. So it's important to frame always, when you think of machine learning success, how do you measure it? Because it's critical. It's very application dependent. In our case, for example, we have many more cleanware apps than malicious apps in the wild. And we also don't want to warn the user that there is a malicious app when there is actually not. So we don't want false positives. So we basically use 2 metrics: precision, how many times I detected malware was actually malware, and recall, how many of the malware we caught. And because we care about both, we use something called the F1 score, which is basically the mean of both. What do you need to imagine for a very good classifier using this metric? This line. So ideally, you would have perfect recall, perfect precision. You go to the upper right corner. That's very good evolution. And this is the results we got. So you can see 3 lines here. You have the baseline classifier that we are trying to improve upon. We have the normal, not federated version of the semi-supervised classifier, very close, of course, improving. And then we have LIM. This is caused by the federation of clients. So by learning from many clients at the same time, you can get a higher performance. But OK, how many false positives? How many times do I get an alert when there's actually no malware application being installed? We also dramatically improve on that. So the baseline classifier does very bad. It gives 7. The vanilla semi-supervised learning does 6, and we go to 1. So we give very few false positives, which is very nice. But OK, this works functionally, but how about security and privacy? What if we have a super strong adversary? 50% of the users are compromised. I'm the NSA and I can hack everybody, 50%. And they all try to do one small thing, make a specific app that is malicious look like clean. And they will compute all the weights in here to make that work, taking into account how everything works. So they have access to all the algorithm and the data of the users that they have compromised. Well, it turns out our defenses stand up very good. So you have here the baseline, no protection, very bad, F1 score very low. This is the poison model, so the adversary is effectively making the models worse in order to make the malicious app become clean to the rest of the classifier. And then you have LIM and the vanilla semi-supervised. You can see the adversary has an effect on the performance of our LIM classifier. But we still manage to get below all the other classifiers. So we are somewhat resistant against poisoning attacks. Why? 2 reasons. We have a private set of data in the cloud, and there is a small attack surface, few parameters, only 5, and there are constraints that they must have to adapt to 1. So yeah, doubly happy. How about privacy? Can we infer which apps users installed by looking at the parameters they sent to the cloud? Well, we see not really. Again, 5 parameters, many apps. How do you pinpoint specifically one app only through 5 parameters? That's not possible. Simply not possible. There is no single success in our testing. So okay, it's only 5 minutes to go. Future challenges. So first, as I already hinted before, performance. So we design everything for security and privacy. Performance is decent, we improve, but it's not optimal. We can improve on that. How can we select these classifiers in the ensemble to provide better performance? Once we have that, integrate it into the real world. So I need a good, high-quality library that is easy to deploy to go to possible customers and say, here you are, use federated learning, security, privacy is strong, and performance-wise awesome. Once we have that, we can evaluate, okay, in a real-world scenario, how does this work? Possible applications. I'm personally very interested in automated grading. I have 2 kids, and I want my kids to benefit from our research. So imagine we have a client model in the student devices, cloud model in the school, or in a set of schools. And we can use LIM as an encoder to generate embeddings. That's for later ChatGPT stuff style, to decode later a grade and a justification for that grade. Another one is very typical fraud detection. So you have banks, they have individual models. They don't want to leak information to other banks. So you have client models in each bank, cloud model in, for example, Swift or whatever association, and then you can detect fraud without leaking information from the banks. And we can also use it for network programmability. So you can accelerate many types of network operations using machine learning to preserve privacy and still be secure. We can use LIM. So to conclude, using new techniques for machine learning can broaden the applicability of existing techniques. In our case, semi-supervised can help federated learning. We can stop inference attacks thanks to the lower dimensionality. We have very few parameters. And poisoning attacks are not that easy in our scenario because we have a private data set that the cloud uses to offset the contribution of the adversary. So that was all from our side. Thank you. And if there is any questions, please.